Hello everyone and welcome to Organic Chemistry. Today I'll give a presentation on alkenes. What are alkenes? Alkenes are compounds that contain carbon-carbon double bond. So for example, the simplest example for alkene has 2 carbons, and remember each carbon must have 4 bonds. So we have 1, 2, and then we're remaining with 2 more, so we add hydrogens. So hydrogen, and here hydrogen and hydrogen. So each carbon has a valence of 4. So that's the simplest alkene. And because it has 2 carbons, alkene with 2 carbons is called ethane. For an alkene, you drop the A and E and change that to E and E. So the name for an alkene is, you change that last part, becomes E and E, alkene. So with 2 carbons, its name now will be ethene. Remember, we drop the A and E and change that to E and E. This is an ethene. Next, hybridization. Hybridization basically refers to the type of orbitals that are used in the molecule. So if you look at an alkene, HC double bond CH, that's the simplest alkene. The carbon here is bonded to 3 things, 1, 2, and 3. So when carbon is bonded to 3 things, that gives what's called sp2 hybrid orbitals. So sp2 hybridized. So actually both carbons, even this other carbon, is sp2 hybridized. Let me spell that correctly. Hybridized. For something to be an sp2 hybridized, it will mean that its geometry is flat, so we say planar, and the bond angle is 120 degrees. So that means this angle here and this angle is 120 degrees and contains a double bond. So has a double bond. So if a carbon has 1 double bond, it will be an sp2 hybridized. So alkene carbons, the double bond carbon is sp2 hybridized. Just as a quick example or a quick review, if you have something that looks like this, here you will see that this is sp2, this is sp2, but these other 2, so that and that, are sp3 hybridized because you actually have 4 bonds on each carbon, and we'll look at that later. Okay, next, skeletal structure. Now this is where we use lines instead of carbons to draw organic molecules. So for example, if you have a CH2, CH2, and then CH, let me put this hydrogen here, so CH, and then double bond carbon, H and H, you'll see that we have carbon number 1, 2, 3, 4, and 5 carbons. We can actually draw a more summarized format, a condensed format. So we call it a skeletal structure, where we only show we show lines for carbons. So before we do the skeletal structure, I'll draw a condensed structure of this. So the condensed structure will be, so carbon number 5 is CH3, and that's connected to number 4, CH2, connected to number 3, CH2, connected to number 2. Number 2 is CH double bond. So sometimes they will put a parenthesis around that, double bond CH2. So that is condensed structure. Next, we draw the skeletal structure, and here we only use lines. So carbon number 5. So that end means it's one carbon, and then each corner will be a carbon. So that's carbon number 4. So carbon number 5, and then that corner will be carbon number 4. This corner will be carbon number 3. Then that carbon corner is carbon number 2. You'll see that carbon number 2 has a double bond to carbon number 1. So we put double bond like that. And we can label the carbons again, 1, 2, 3, 4, and 5. So that is a skeletal structure. Next, we look at cis and trans isomers. Because you have a carbon-carbon double bond, there is no rotation between the carbon-carbon double bond. Because you have a double bond, it blocks rotation. And because of that, you have two possibilities. You could have one situation where both groups on carbon are facing up or down, so both groups facing down. So you see, it's an alkene, but both groups are either facing up or down, and that is called cis isomer. So these two are called cis. And the easiest way to remember that is if somebody pointed a gun at somebody and told him to freeze, they will lift up both hands. So that's cis isomer, both groups up or both groups down. The other type of possibility is where one group is up and the other group is down. You have one group is up, another group is down, or the opposite. Still you have one group up and one group down, and that actually looks like it's going through, like that. It's going through. So we say trans isomer. So trans alkenes have on either side of the double bond, one group is going up and the other one is going down. Next, we look at E and Z alkenes. So E and Z alkenes. We saw up there on number 4 that it's very easy to tell if something is a cis or trans just by looking at where the groups on either side of the double bonds are facing. If they're both up or down, that's cis. If one is up, the other one is down, then that becomes trans. What if you have a mixture? So for example, you have an alkene here like that, and then you have that. If you look at the double bond here, we have this group up and this group up, but this other one is going down. So you can't say both groups are up or one group is up and the other one is down. In this situation, we cannot use cis and trans. So we need to use a different method, and that's where the two classification system comes about, the E and Z isomer. So E and Z is used when you cannot use cis and trans. Just before we continue, this carbon here has a hydrogen. It's not shown. First of all, number 1, you have to divide the double bond like that. So you cut the double bond into 2, and then you focus on the left-hand side of the double bond. If you focus on the left-hand side of the double bond, this is a carbon. So that's a carbon. The mass of carbon is 12. And this one here is a hydrogen. The mass of hydrogen is 1. Because of that, we say carbon has a higher priority than hydrogen, and therefore we assign it number 1 and then number 2 for the lower priority. So we finish with the left-hand side. Then we move to the right-hand side, and then we do the same thing here. First of all, you have a carbon here, and here you have a carbon connected to another carbon. So this will have a higher priority. So this side here has higher priority, and because of that, we're going to assign this as number 2 because it's lower priority, and this side as number 1 because it has a higher priority. We end up with something that looks like this. So if you just focus on the high priority groups, you'll see that you have high priority on the left-hand side going up and high priority on the right-hand side going down. So it almost looks like what you will call a trans, but now we're focused on priority. If the high priority groups are opposite, then we label that E isomer. So this is an E isomer. If the high priority groups are on the same side, then we'll label that as a Z isomer. So Z isomer, the easiest way to remember it is ZEM-Zide. That means the high priority groups, that's group number 1 on the left and number 1 on the right, are both on the same side. So they are both either up or they're both either down. They're almost like what you will call a cis isomer, but now we focus on priority. Now again, I'll go into naming of alkenes. Look for the longest chain, and that becomes the parent name. Parent name goes to the end of the name. So if you look at the longest chain, is 1, 2, 3, 4, 5, 6, and 7. That's if we start from there, and then here is 1, 2, 3, 4, 5, 6, and 7, same number. And then the last option is 1, 2, and 3. That's 3 carbons. So that's really not long. So the longest priority is number 1 to 7. You have another option, counting from the left-hand side. 1, 2, 3, 4, 5, 6, 7, or 6, 7 on the other side. It still gives you the same number of carbons, 7. However, you want to focus on where the double bond is. Look at the double bond right here. If we start counting from the left, see 1, 2, 3, 4. It means the position of the double bond will be position number 4. However, if we start counting from the right, starting from here, like that, so 1, 2, and 3. So the position will be 3. So that means the counting from the right will be favored because we want the lowest position for the double bond. So number 2, number in such a way that you have the lowest position for the double bond. Lowest double bond position. And then number 3, assign the side groups. In this case, if we choose the main chain to be here, 1, 2, 3, 4, 5, 6, and 7, then we see that there is one side. There is a group here that has not been included as part of the chain, and that group has 1 carbon. That's really a CH3, and therefore we call that a methyl group. So the side group is methyl, and that methyl is on position number 2. So it becomes 2-methyl. So we want to put the parent name, the longest chain, because it's 7, it's supposed to be heptane. But remember, we drop the last A and E and change that to E and E, so it becomes heptene. So we put them together, the side group plus the parent name, and therefore the name for this compound will be 2-methyl, and then space heptene. If you have several side groups, then you need to indicate the position and say how many of those groups are there. So let me just give you a quick example. The lowest numbering system, so 1, 2, 3, 4, 5, 6. Let's show the position of the double bond. The double bond is right there, so that the double bond is on position number 2. And because it has 6, the parent name becomes hexene. That's the parent name. But now we need to list the groups, the side groups. We have 1 here, so that's 2-methyl. Then we have another group here, that's 4-methyl. And then we have a 2-carbon group there on position number 3, so that's 3-ethyl group. Now we want to list them alphabetically. We have ethyl and we have methyl. So E comes before M in the alphabetical order. So we want to start with 3-ethyl. So the name becomes 3-ethyl, and then you put a hyphen to show the other side group. We have on position number 2 and position number 4 is the same group, methyl. So you say 2, 4 di methyl. And then we have another side group, the ethyl group. So 3-ethyl. And then the parent name, hexene. Thank you very much. We'll continue on the next lesson where we will look at Markovnikov and anti-Markovnikov addition.